Good morning, this is class 8 of the module nuclear reactions. Today we are going to learn about compound nucleus reactions. About compound nucleus we have already discussed in our early classes. That is, let's once again go through the fundamentals. Suppose that an incident particle enters a target nucleus with an impact parameter small compared to the nuclear radius. It then will have a probability of interacting with one of the nucleons. Nucleons means either protons or neutrons of the target, possibly through a simple scattering. So you are supposing that a particle is incident on a target nucleus. That incident particle, suppose that it interacts with one or more nucleons present in the target nucleus. In doing so, there will be a nucleon recoiling. That nucleon recoiling will include the transfer of momentum. So the recoiling struck nucleon and the incident particle will again make collisions with other nucleons, and after such collisions or interactions, the incident energy, a part of the incident energy, will be shared among the nucleons of the combined system of projectile plus target. Now the average increase in energy of a single nucleon, it is not that much enough to free it from the nucleus. So there will be a statistical distribution in energies and a small probability for a single nucleon to gain a large enough share of energy to escape. So it is in order to escape, it requires large amount of energy. Now such reactions have a definite intermediate state after the absorption of the incident particle but before the emission of the outgoing particle. That intermediate state is called compound nucleus. So this is the part that you have to study. What is a compound nucleus? That is, we have already discussed about how the interactions occur and such reactions having an intermediate state. That is a state just after the absorption of the incident particle but before the emission of outgoing particle. It is called, that intermediate state is called compound nucleus. It is represented by A plus X is equal giving Y plus B, that is the reaction. So in between this reaction you will get an intermediate state that is represented by C star C. This indicates the compound nucleus, this one. Now you are going to consider a reaction that proceeds through the compound nucleus to be a two-step process. One is the formation and then the subsequent decay of the compound nucleus. That is, a given compound nucleus can decay in many ways, and essential to the compound nucleus model of nuclear reaction is the assumption that, here we are going to make an assumption that relative probability for decay into any specific state of final products is independent of means of formation of the compound nucleus. That is, the decay probability depends only on total energy given to the system. In effect, or as a result, the compound nucleus just forgets about the process of formation and the process of forming from the intermediate parts, and decay is governed primarily by statistical rules. That is, it just forgets about the process of formation. Here they have given an example showing the decay of the compound nucleus zinc. That is, it can be formed through various reactions, and this actually shows the various ways in which it is formed, and this shows the various ways in which it decays. So this example, if you want, you can just read through. No need of mentioning in your essay part. If it's easy, you can just write. Otherwise, you can skip. Here the compound nucleus zinc can be formed through various reaction processes, and they have shown the various process of formation and the various process of decaying of the compound nucleus zinc. Now the compound nucleus model works best for low incident energy. So this model is applicable only at low incident energies, that is energy between 10 to 20 mega electron volt, where incident projectile has a small chance of escaping from the nucleus. And another energy range, another factor at which it works very well is in the medium weight and heavy nucleus. Here the nuclear interior will be large enough to absorb incident energy. So compound nucleus model works very well at two conditions. One is at low, you can skip, but this points and all you have to write this one. Now another characteristics of compound nucleus reaction is the angular distribution of products. Now we know there is a random interaction among the nucleons, so we expect the outgoing particle to be emitted with a isotropic angular distribution, that is same in all directions. In cases in which a heavy ion is in the incident particle, that is suppose that the incident particle is a heavy ion, then large amount of angular momentum will be transferred to the compound nucleus, and to extract that angular momentum, emitted particle will be emitted at right angles to the angular momentum, that is mainly at angle 0 and 180 degree. Whereas for light projectile, this is for heavy projectiles. For light projectile, this effect is negligible. So the more the energy that we give to the compound nucleus, the more particles will be ejected. Now the cross section of the final state will be almost Gaussian shape. For each reaction, the cross section increases to a maximum and then decreases as the higher energy makes it more likely for an additional neutron to be emitted. So this slide talks about the characteristics of compound nucleus reaction. So when you are asked a question, compound nucleus reaction, discuss about that. Just mention the definition. This slide you have to write. This example you can skip, but you have to write starting from here the characteristics and also this particular slide. Okay. Next one is direct reactions. Now direct reaction stands at the opposite end of compound nucleus reactions, and they are also called direct reactions. Here also called peripheral process. As the energy of the incident particle is increased, its de Broglie wavelength decreases until it becomes more likely to interact with a nucleon sized object than with a nucleus sized object. So what is meant by direct reactions? That is a question. Direct reactions are also called peripheral reactions. They are those reactions in which incident particle interacts at the surface of the target nucleus. Now a 20 megaelectron nucleon has a de Broglie wavelength of about 1 Fermi meter and it can participate in direct process. Direct process mostly involve one nucleon or very few valence nucleon near the surface of the target nucleus. Now these are some of the characteristics. They occur very rapidly in a time duration of 10 raised to minus 22 seconds, whereas compound nucleus reactions take more time, that is between 10 raised to minus 16 to 10 raised to minus 18 seconds, and that additional time is necessary for the distribution and reconcentration of the incident energy. Second point, the angular distribution of outgoing particles is a direct reaction tend to be more sharply peaked than in case of compound nucleus reaction. So these 2 points you have to write. These are the characteristics that distinguish a direct process from compound nucleus process. Okay. Now inelastic scattering can proceed either in a direct process or in an indirect process. They mainly depend on the energy of the incident particle, in which a single proton is transferred from projectile to target. So here you will get a question, what is meant by deuteron stripping reaction. Okay. Now another deuteron stripping reaction is here they have mentioned about the interaction between deuteron and neutron, that is DN. Now this is deuteron and proton. They occur through a direct process just like evaporation. Then another one is alpha particle and neutron reaction. That is also a direct process. Then now one important application of single particle transfer reaction, that is DP and DN, is a study of low-lying shell model excited states. We know several states will be populated in a reaction, so we can choose a particular state from the energy of outgoing nucleon. Once we have found out that energy of that particular state, it will be very easy for us to determine just which shell model state it is. For this, what we need to do is just find the angular distribution of emitted particles, and that will give you spin and parity of the state that it is populated in a particular reaction. Here they have discussed in detail about the how to find all those things, that is consider the angular momentum transfer in a neutron stripping reaction. So geometry is given here. An instant particle with momentum PA gives outgoing particle with the momentum PB. The residual nucleus will recoil with momentum PA and that it must be placed in an orbit with angular momentum L equal to Rp. Now momentum vectors are related by these laws. That is, it is just enough to write P square equals this one. Once you know the energy of the incident and outgoing particle, then we then have a direct relationship between L and theta. That is, particle emerging at a given angle should correspond to a specific angular momentum of the orbiting particle. Now they are mentioning about the same example that have discussed. Now there will be interferences between the scatterings. So because due to the scatterings occurring at the opposite end of the nucleus, there will be interference effects. These interference effects will give you maxima and minima in the angular distributions. So this experiment, if you want, you can skip, but after that you can just write this sentence. Now the angular momentum transfer gives us a change in parity of reactions. That also you can write. That is, L will be equal to even for no change in parity, and L will be equal to odd for a change in parity. Okay, that much is enough. No need of writing this. Then they are discussing about transition amplitude. That is, what is the transition amplitude for a system to go from initial state x plus a to final state y plus b. It is governed by a quantum mechanical matrix element M. It is given by this formula. Here the interaction V is in which this wave function related to psi A and psi B are considered as plane waves. Using a spherical wave expansion and making the simplifying assumption that here we have made an assumption that interaction takes place on the nucleus surface. So integral is evaluated only at r equal to r. Now taking this calculation one step further, we use the optical model to account for the fact that incoming and outgoing plane waves are changed are changed by the nucleus. This gives the distorted wave-borne approximation, or DWBA. Since there are no pure shell model states, the calculated cross-section will describe many different final states. Each of these states will have a differential cross-section whose shape is calculated based on the model, that is DWBA. But amplitude of cross-section depends on fraction of pure shell model state included in the wave function for that state. The measured cross section is thus reduced from the calculated shell model single particle value by a number between 0 and 1 and is called spectroscopic factor S. D sigma by d omega measured will be equal to S d sigma by d omega calculated. A pure shell model will have S equal to 1. But actually in practice we find shell model wave function to be distributed over many states. So what is direct reaction? This one you have to write. The two characteristics you have to write. Then just mention about neutron stripping reaction and single particle transfer reaction and what is its use. So this slide, I think it is easy. This you can write. This experiment you can skip, no need of mentioning. But after that you have to write this sentence and from here this one. Okay. Then this one also if it is an essay question you can add this 2 slides also. Okay, that is enough. That experiment you can skip. Okay, so study accordingly. Thank you.